Okay, it looks like we are at the 2 o'clock time, and certainly people will continue to filter in. We're already up to 40 participants. That's great to see. Whoops. If you do pop in and you are unmuted, please go ahead and mute yourself. I've tried to catch everybody as they come in, but we all know how computers work sometimes. Sometimes they do what they want and not what we want. So I am Thomas Reynolds. I am the interim director of the Louisiana Scholars College at Northwestern State University in Natchitoches, Louisiana. For those of you who don't know where Natchitoches, Louisiana is, it's in the northwest corner of Louisiana, home of the very famous movie Steel Magnolias, if you want to put a face to the name. We are very excited today as part of World Logic Day 2021 to welcome Martin Davis, Emeritus Professor from NYU, to present our keynote address, Algorithms, Equations, and Logic. And I will pass it over to our Professor of Mathematics here in the Scholars College, Alexei Muravitsky, to introduce Martin.
Thank you. I would like to say a couple of words about our distinguished guest speaker today. Well, actually, my introduction, I just watched the presentation of Professor of Computer Science at Rice University, Moshe Vardi, who called our speaker a distinguished logician. And I just want to join to this characteristic. However, I want to add a few words. I want to say that he was awarded the Lester R. Ford Award in 1974 for his work on Hilbert's 10th problem. In 1975, he won the Leroy P. Steele Prize, awarded by the American Mathematical Society for distinguished research work and writing in the field of mathematics. And the same year, he shared the Chevalier Prize with Reuben Hirsch, awarded by Mathematical Association of America for outstanding expository article on a mathematical topic. Also, he is a co-author of Matisevich-Robinson-Davis-Putnam Theorem, and he is also known for Davis-Putnam algorithm, or sometimes known as Davis-Putnam method. Well, these well-known facts you can find on the internet, in Wikipedia, for example, but I would like to add a couple of more facts about our speaker, which are not widely known to logicians, at least. Together with Melvin Hausner, he co-authored the translation of a classic book on mathematical analysis, differential and integral calculus by Edmund Landau. And also he is the author of first course in functional analysis, a very good short introductory book. Well, this is a copy. Short and very well written. And a couple more things. According to the Mathematics Genealogy Project, Emil Post did not have doctoral students. That was simply because there was no PhD program at the City College of New York when Post worked there. Well, our speaker, as he once told me, was an undergraduate student at that time and took classes with Post. And I believe Post had a profound impact on the young man. And last but not least, since 2002, our speaker has been the moderator of the forum, a closed, moderated email list for discussing foundations of mathematics. Now let me invite our speaker, Martin Davis. Welcome.
Thank you, Alexei. Thank you very much for that introduction. You're correct about the influence of Post on my life. Knowing him as a young man had a really profound effect on me. He was a wonderful mathematician. Well, this is International Logic Day, and I'm very grateful for a chance to share some of my ideas and views. The talk I'm giving is really meant to be understandable by a very wide audience. I'm not assuming that people out there know anything about the subjects I'm talking about. So forgive me if some of what I say seems too elementary to you. Just to make matters definite, the discussion all will involve the natural numbers, the numbers used in counting, and I'm including 0, 0, 1, 2, 3, so on. The idea that I'm going to be basing everything on is the need to specify sets. It's easy to make sets of numbers, and if I say the numbers 2, 3, 7, and 19, I don't have any problems about how to specify them. I just give them to you. But you can't always do that. There might be just too many numbers in the list to try to list them all. You could write them down, but maybe there are so many that they wouldn't fit on a page, or maybe even not even in a book. And there are infinite sets of numbers, and of course you can't possibly list all of them. So you want ways to specify this is the particular set so that people know what set you're talking about, which things are in the set and which aren't. And we're going to look at 3 different ways to do that by using an algorithm that decides membership in the set, an algorithm that lists all the members of the set, and parameter values for which an equation has solutions. I'll explain all this in more detail later, so don't worry if you don't quite catch it all at this point. But they're really very remarkable results that come from looking at those 3 methods and how they relate to one another. I'll start with a very simple example, a set of even numbers. That's an infinite set, and indicated there is 0, 2, 4, ... But as Alexei mentioned, my being a partial translator of Edmund Landau's calculus book, he warns you right at the beginning that when you specify an infinite set that way, you're really not specifying it at all. Of course, We all understand that after 4 comes 6 and after 6 comes 8, but it doesn't have to. Maybe the set you're thinking of, after 4 comes 17. So we do need other ways. Did I go too far? No. Okay, here's an algorithm to decide membership in this set. Divide the number by 2. When you do a division like that, you get a remainder. If the remainder is 0, the number is even. If the remainder is not 0, and it's odd. So that works. An algorithm to list members. Well, we start with 0, and we just keep adding 2. 0 plus 2 is 2, plus 2 is 4, plus 2 is 6, plus 2 is 8. So these are two different ways to specify the set. Here is the third way. Here's an equation: a minus 2x equals 0. Remember, we're looking only at natural numbers, so forget about fractions. So if this equation has a solution for x is the unknown, a is the so-called parameter. If for a particular a, the equation has a solution. For example, if a equals 6, x equals 3 is a solution. If a is odd, if a is 7, there is no natural number x that makes it 0. So this equation specifies the same set, the set of even numbers, as the set of values of the parameter for which the equation has solutions for the unknown variables. And I'll use the usual convention where parameters are letters near the beginning of the alphabet, and unknowns, I use letters like X, Y, Z near the end of the alphabet. We'll say that a set is decidable if there's an algorithm for deciding membership in it, that it's listable if there's an algorithm that lists the numbers. And the caveat in parentheses is really crucial here. When we, for listability, they don't have to come in any particular order. All we ask is that for values of the parameter that are in the set, there is a solution, and for ones that aren't in the set, there is no solution. But the list can produce these numbers in any order, and so on. Finally, a set is, a set is Diophantine if there's an equation with a parameter n and unknowns, any number of variables x, y, z, which has a natural number solution for just the values of a that are members of the set. So we have these three notions: decidability, listability, and being Diophantine. One more example, a somewhat less trivial one than the even numbers, the famous Fibonacci numbers. You start with 0 and 1, and you get the next Fibonacci number always by adding the previous two. So 0 plus 1 is 1. 1 plus 2 is 3. 3 plus 5 is 8. And the next one will be 13, and so on. Here's an algorithm to list members of the set. We're looking at the list algorithm first. Start with 0 and 1 and repeatedly add ask the last two numbers of the list to get the next one. Just what I had said before, but now it's made explicit as an algorithm. Algorithm to decide membership in this set. We'll do the same thing. Start with 0 and 1 and repeatedly add the previous two numbers to get the next number. But you keep doing this only a finite number of times. One of two things will happen. Either you will hit the number you're looking at. If I want to know if 17 is a Fibonacci number, I start making the Fibonacci numbers, and when I get to 21, I know that 17 is not a Fibonacci number because it's been passed by. This is an example where the same algorithm is being used for making the list as for deciding. That only works because the listing algorithm generates the numbers in order of size. So you know that once you get to one that's bigger than the number you're looking for, it's not in the set. That will not work if that will not work if the listing algorithm does not produce it in order of size. An algorithm to specify the set as parametric values. Well, this is a more complicated set. It's a more complicated solution. An equation which works, well, this is really two equations. X squared minus ax minus a squared equals plus or minus 1. Well, you can make it into one equation by squaring both sides. So here is the equation that for values of the parameter a have a solution x if and only if a is a Fibonacci number. Here's I'm obviously not going to prove that in this talk, but here is some data that sort of indicates it. In the A column on the left, the Fibonacci numbers are all bold, and in each case, the values of x that do produce plus or minus 1 are shown. They turn out also to be the Fibonacci numbers, but that's certainly not required for the definition. It's just one of the many fascinating properties of the Fibonacci numbers. So I recall what I've said so far. The set of natural numbers is decidable if there's an algorithm that decides membership. It's listable if there's an algorithm that makes a list. And it's Diophantine if there's an equation with a parameter and unknowns which has solutions just for the values that are members of the list. Well, the sets we've looked at so far have all three of these properties. The even numbers and the Fibonacci numbers are decidable, they're listable, and they're Diophantine. But we are entitled to ask, is that always going to be the same? Do these come together or are they different? What is the relationship among these three ways of specifying a set of natural numbers? And now we'll talk about that. The first thing we notice is that every decidable set is listable. If a set is decidable, it is also listable. So if we have a decidable, if we have a decidable set, how do we make a list? Well, it's clear. We start with the full list of natural numbers. I neglected to put 0 in. I should have included it. I just try each number 0, 1, 2, 3, and so on, and test it. If the test set is in the set, I put it on the list. The set is not in the set, I don't put it on the list. So decidability can be used to make a list. Notice that it's not obvious that the converse of this would be true. It's by no means obvious that a listable set has to be decidable. Maybe it's not. If you're looking to see whether the number 17 is in the set and all you have is a set making a list, and you've watched it, and the computer has printed out 100 numbers and none of them are 17, you still don't know whether or not 17 is in the set. Maybe you need to wait for 200 numbers, or maybe it never will show up. So there's a complicated relationship there. Every Diophantine set is listable. You can if you have the equation, so you have the parameter a and a certain number of unknowns. Let's say there are just two, x and y. Then you can make a list to start with of all the possible triples of values of a and the parameters x and y. Here you can see how the list, one way to make such a list. First, all the ones that add up to 0, then all the ones that add up to 1, then all the ones that add up to 2. In each case, there are only finite many, so you can make such a list. And then you can test each of these triples in the equation. And if x and y satisfy the equation, then a is in the list. And if they don't, you go on to the next. If instead of just two unknowns, there are more unknowns, the same technique will work. You just have a more complicated list of tuples, that's all. If there are 5 unknowns, you'll have 6 tuples. But this is a general method that will work. Notice, by the way, that this algorithm is not a decision. It does not decide membership in the set. It's perfectly possible to have a small value of the parameter. It might be that 2 is in the set or 5 is in the set, but you need values of the unknown that are enormous numbers to satisfy the equation. So you won't find out until the algorithm runs for a long, long, long time. The complement of a set of natural numbers is just the set of all numbers that aren't in the set. So the complement of the even numbers is the odd numbers. If a set and its complement are both listable, then the set is decidable. Just the set being listable by itself is not enough to make it decidable. But if the complement is also listable, then it is. And that's easy to see why that's true. If you just start the listing algorithms for both the set and the one for its complement, you let them both run and you watch what they put on the list. Any number has to either be in the set or in the complement. So you have a guarantee that if you wait long enough, the number will turn up in one of the two lists, one and only one of the two lists. And that'll tell you whether the set number is in the set or it's not in the set. Notice that this is an algorithm, but not a wonderful algorithm. You have no bounds on how long it'll take you to find. You know that you'll eventually find out, but eventually might be reserved for your great 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 grandchild to find out, because you might long be gone before one of the two lists has the number you're interested in on it. Okay, now we have come to so far everything I've said is understandable in its own terms in a pretty direct way. But now this is a fairly deep theorem, which I put due to Church, Turing, and to Post, who Alexei kindly mentioned. I should mention also that Alonzo Church was my dissertation advisor, and he was also Turing's dissertation advisor, though Turing had proved this before he met Church. There is a listable set whose complement is not listable. Neither K nor its complement is decidable. There is such a set. And I won't be able to tell you how to prove it, but I will make use of it a great deal. So there's a particular listable set. And I should say that the proof of this is entirely constructive. The algorithm to produce the list is one that can be provided quite explicitly. And now the theorem that Alexei mentioned, variously called the MRDP theorem, the DPRM theorem, or Matyusevich's theorem. Yuri Matyusevich himself calls it the DPRM theorem. The initials are, M is for Matyusevich himself, R is for Julia Robinson, D is for me, and P is for Hillary Putnam. And there was a 20-year history of work before this theorem. One had a proof of this theorem, and Yuri Matyusevich supplied the essential final step with a very beautiful proof. So every listable set is Diophantine. If you have an algorithm for listing a set, there's also an equation whose parameter values with where there's a solution for the unknowns is exactly the same set. And I should say this: the proof of this is also entirely constructible. There's a entirely constructive way of turning an algorithm for listing a set into an polynomial equation. This is a picture of three of those four people. Yuri Matyasevich is on the right. Julia, of course, is the one in the middle. And that's me with a lot more hair on my head than I have these days. This photograph was taken in Calgary, California, when Yuri had permission to leave the Soviet Union and go to Canada, but not to the US. So Julia and I separately flew to Calgary, Canada, so we could be with Yuri briefly while he was on a visit there. So let me recapitulate what we've done so far. We have the unsolvability theorem. There's a listable set K whose complement is not listable. Neither K nor its complement is decidable. And we have this MRDP theorem. Every listable set is also Diophantine. Now, there's a corollary that follows from that. If every listable set is Diophantine and K is a listable set, K must be Diophantine. So there's an equation called the K equation, and I'm going to make use. So far, I've covered algorithms and equations, but I haven't talked about logic yet. But I will apply this corollary to logic. There's an equation, the K equation, with parameter A and unknowns, such that there's no algorithm that can tell for a given value of A whether that equation has a solution in natural numbers. That's because if there were such an algorithm, we could use it to test for membership in K, and there is no such algorithm. You may want to know how many unknowns do you need. If you wanted to produce an equation that you could actually write on one printed page, you would need something like 24 unknowns, 24 or 25. If you were willing to, if you just said forget about anything, but just how many are the least you can get away with, Yuri and Julia managed to show you could get away with 13 of them, and then Yuri improved that further to just 9. So, but the exponent in the polynomial will be astronomically large in order to attain that result. Anyhow, there is such an explicit equation, and we'll assume we have one of them and we can work with it. We should mention, incidentally, the connection with the Hilbert problems. David Hilbert in 1900 gave a speech welcoming the new 20th century with a list of 23 problems that there was no real handle on in 1900. and posing them as the problems for the future. The 10th problem was to find an algorithm for equations that have, whether equations have integer solutions. And it follows from this that there is no such algorithm. So we have found we have solved Hilbert's 10th problem by giving a solution of the form there is no such algorithm. I'm not ready to show you that yet. Okay, now I turn to logic. Well, what is logic? Logic is something that we use in when we reason and infer from in various ways. Now, some people think that it's a valid reasoning principle that if the president of the United States says something, that thing must be true. That is not a principle of logic, I promise you. In fact, principles of logic don't tell you explicitly that any of the things you're interested in are true or not. All it does is tell you that if certain things are true, other things are true at all. What is remarkable is that starting by assuming that certain very simple looking things are true, you can prove using purely logical inferences that some rather complicated relationships you would never have imagined are also true. Euclid showed that starting with statements like that any 2 points you can make a line between them, and some things about parallel lines, you could prove the Pythagorean theorem that in a right triangle, the hypotenuse squared is the sum of the squares on the side, which is not obvious at all. In the late 19th century and running very much into the 20th, people raised the question of could what Euclid did for geometry be done for mathematics as a whole? Could you start with some very simple things of a purely logical nature and end up with all of mathematics? Gottlob Frege was really the first to try to do this, actually, and he produced a monumental work, really, the Grundgesetze der Mathematik, in which he carried it all out. Unfortunately for him, Bertrand Russell proved that his system was inconsistent. And poor Frege had to write a supplement to the second volume of this work, which was already at the printer, saying the worst thing that can happen to a scientist is to have his work collapse just as it is complete. A letter I got from Bertrand Russell, put me in that position. Well, Bertrand Russell got together with his colleague Alfred North Whitehead and tried basically to do what Frege did, but not run into contradictions. And they produced a work in 3 rather massive volumes. If you could see me instead of my slides, and you looked behind me in the bookcase behind me, you would see the 3 volumes of Whitehead and Principia and Whitehead and Russell's Principia Mathematica sitting there, in which they start with logical principles like if P implies Q is true and P is true, then Q must also be true. And other things that, well, maybe they're not quite logical principles, like there are sets that are infinite. Uh, they were able to start with things like that and end up with doing things that were actually mathematics without anyone being able to point to such a clear line to say the logic ended here and the mathematics starts there. What I showed you briefly was a page from Principia Mathematica. There are various things I wanted to point out about it. I know you can't see it very clearly in this. First of all, that very little of it is in English. An awful lot is in their own logical language. Uh, the other thing I wanted to point out is that there is actually a mathematical theorem that they finally got to. This is, no one will doubt that this statement 1 + 1 = 2 is a theorem of mathematics. If not a very profound one, it is a true mathematical theorem, and they have proved it following their own rules. The other thing I wanted to point out is the number here. If you can see that, the number is 88. It's taken 88 pages of them of hard work to get there. It's really worse than that, because now I have to tell you or confess to you that it's page 88 of volume 2. So a whole big fat book goes by before even they begin to talk about numbers. This is their achievement. Their achievement was great. It was a wonderful achievement, but it was what engineers would call a proof of concept. It's a sort of really a ponderous mess. But there are very neat systems, in fact, that have been developed, and a number of them exist in the form of computer implementations, and proofs in purely logical formal languages have been presented of some very deep theorems, not 1 + 1 = 2, but the prime number theorem, for example. From our point, I can't really talk about those things at all with this talk, at least in part because I'm pretty ignorant about a lot of it. I was involved in some of the very beginning of some of that work, but it's gone way beyond me. But there's one simple thing they all have in common that I do want to call upon, and that's their algorithmic nature. I said they're computer implemented. That means they're implementing out. There's an algorithm to implement. The algorithms can all be thought of in the following way: that what you can you can imagine that it wouldn't be used this way, of course, but you could imagine that the algorithm is started and it starts generating theorems that it's proving, and just watch, and it proves it and proves it. It's a list. It's a listable algorithm of theorem. A listable list. I'm sorry. It generates a list of theorem. Now, just using that about formological systems, one can say some very interesting things. We're going to want to apply the K equation to formological systems. One thing about the formological systems that I've been talking about is they talk about various parts of mathematics. And, they'll be generating theorems in topology, analysis, whatever, but they certainly can deal with equations in natural numbers. For example, if we look at the Fibonacci equation that I listed here again, suppose that you want to express in the language that the equation has no solutions. In other words, that A is not a Fibonacci number. Here I am assuming that the language is using these particular symbols, the upside down A to mean every. So it says that for every x squared minus ax minus x squared, the whole thing squared isn't equal to 1. And suppose that we're now looking at this actual expression, or at least the one represented in the formal language we're thinking of, that could stand for that statement. So, for example, when A is when A is 4, the equation has no solution, so the statement is true. But if it's 5, I don't know why the slide isn't showing the bottom line. For 3, it's false because 5 is a solution. 3 is a Fibonacci number. Okay, but we want to apply that not to this equation, which is not very interesting, but to the K equation. So here's the K equation. We have no idea. It's got lots of unknowns. I'm not going to write even 9 unknowns down there. I just write 3. And so there is this K equation that we said has no algorithm that can tell for a given value of A whether or not that equation has a solution in natural numbers. So again, we imagine we're looking at the representation of these statements in whatever formal language is being used for the particular system. And we look at this infinite sequence of equations. So each one says that a particular number is not has no solution. Okay. So now let's look at our formological system from the outside and talk about it. One of the things we would like a logical system to be is sound. That is, we would like to believe that the things that it proves are all true, not like the things that a president says. We call a logical system complete if all the true statements that it expresses are true. Well, we can even make that narrower and say we'll call it complete if every statement it makes about solutions of a polynomial equation are true. Now we get a really important theorem, Gödel's incompleteness theorem. No formological system can be both sound and complete. That's because if it's sound, there'll be an unprovable expression, such the statement that it represents is true. Proof: if the system were both sound and complete, we could use it to provide an algorithm to tell for a given number A whether the equation has a solution with a number or not. We would just let the formal systems churn out theorems, and sooner or later it will have to tell us either that that is true or that it's not true for that value of A, and that will tell us, that will show that K would be decidable, even though we know K is not decidable. So we see that starting out with simplest sorts of considerations about specifying natural numbers ends up with a rather deep theorem, one that is quite famous and has all sorts of philosophical implications, and is a very appropriate note to end on for a talk on World International Logic Day. Thank you very much.